This is what I said.
Come on.
Yeah, every time. All right. So last time we did that big long branch covering example. Today I'm going to present some sort of standard stuff about trisections, reducibility, stabilization. Thanks for you guys. All right. So let's dive in. So here are two trisections, T1 and T2, for four manifolds x1, x2. We can get a trisection for the connected sum by choosing the connected sum points sigma 1 and sigma 2. Then the connected sum of the trisections is just the connected sum of all the pieces. Well, it's the connected sum of the surfaces, the boundary connected sum of the flanges, and the boundary connected sum of the sectors. So let's just sketch an example to see how it works. I think this one froze. So we'll take our two favorite trisections. CP2 and for S2 plus S2. And we can sum them together. And we get the connected sum of diagrams. Just as you might expect. And so this is a diagram for CP2 connects sum S2 plus S2, which it turns out is diffeomorphic to CP2 connects sum CP2 connects sum CP2 bar. So a couple of exercises. So the first exercise is, I guess I'll just pose it as a question. Why doesn't the resulting diagram depend on the choice of connected sum points? So here I've sort of just obviously chosen points right here, and I've done the summing there. But I may have chosen a point in here to do the connected sum, or anywhere really. In particular, if the curves cut the surface into regions, then it's not so clear why choosing a point to lie in a different region doesn't make a difference. That's exercise. And then exercise 2 is show that the obvious trisections coming from, on one hand, CP2 connects sum S2 plus S2, and on the other hand, this other guy I said, are diffeomorphic. And so I could have also made this by taking 2 copies of this and 1 copy of the mirror and summing them together to also get a genus 3 trisection. And you can actually show that those 2 trisections are the same using slides and such. right. Okay, any questions, comments? So definition, we've already seen this before, but I'll say it again, since we have a little bit more context now. A reducing curve for a trisection, or equivalently for a trisection diagram, is a curve delta sitting inside our trisection surface, such that delta bounds a disk in each of the handle bodies H sub I. And then that's the definition for a trisection. The corresponding definition for a trisection diagram is a curve delta sitting in sigma minus alpha 1 union alpha 2. Maybe I'll call them betas alpha 2. Okay, so a reducing curve for a trisection, for a core surface in a trisection, is a curve that bounds in all three flanges. And for a diagram, it's a curve that you can draw in the complement of the curves. I guess I should say that it needs to be essential. So let's make this an essential, and then curve means simple closed curve. So this is also an essential. Okay, so in this diagram, we have an example of a reducing curve right here. So because I could draw this in the complement of all three colors, and because it's an essential curve, I know that it bounds a disk in each of the handle bodies. Is that what you're thinking about?
Just thinking it's the essential of the complement of the other ones.
Oh, I mean essential on the surface. Yeah. Right. The only other thing it could be is null homotopic. Yeah. Yeah, that's how I use it. And I guess that's probably the same as essential in the complement curves. Well, you have to be a little careful there because I do want to allow like it could be parallel to curves, right? Like in the diagram for S1 cross S3, we have this picture, right? So this curve is actually, they're all the same curve, but because we consider simple curves are simple closed curves. Ice can be positive simple closed curves. But this is a reducing curve, so I guess that's essential within the complement curve since it's an annular, so it's bound to be parallel. Anyway. Okay, good. All right, so now we can state a fun conjecture that you should all run out and try to prove, which is that every trisection of a reducible four-manifold is reducible. I guess I should say that a trisection is reducible if it has a reducing curve. And a four-manifold is reducible if it can be split as a non-trivial connected sum of two four-manifolds, where one of the pieces is not S4. So this is like Hawkins' lemma, right? Hawkins' lemma told us that if the three-manifold was reducible, then we could find a curve on the Haggard surface that bounded in both handle this reducing curve. And so this is sort of like Hawkins' conjecture for trisections. Now, I guess it should be pointed out that you want to be a little bit careful because potentially we can have, for example, S4 split as X1 union X2, where Xi are homotopy forces, are exotic forces. All right, so this is Schoenflies conjecture, right? Because we would have this 3-sphere embedded in S4 that doesn't bound the ball to either side. So in particular, if this conjecture is true, it would imply that if we had a splitting like this, every trisection of S4 would need to be reducible. In particular, the genus 0 trisection would need to be reducible, which would mean the only way S4 could split as a connected sum would be as 2 copies of S4. So this conjecture implies the Schoenflies conjecture. And then I always have to think about whether this is the direction that implies the Poincare conjecture. And I can't do it. It's not. It's not the direction it was. Okay, let's do it. Schoenflies conjecture should be easier to prove than the Poincare conjecture. If Schoenflies is false, if we have this, then we can take say X1 and glue on a 4 ball. Well, I mean these were already exotic spheres, but yeah, sorry. If Schoenflies is false, then already we have exotic spheres. So Poincare conjecture implies Schoenflies conjecture. So implying Schoenflies conjecture does not necessarily imply Poincare conjecture. Okay. Okay, so any questions about that? So more concretely, we can actually state some things we do know. So the first result Alex and I proved is that there is a unique genus 2 trisection. And it's this one, which we've already seen. Okay. And so I guess this is also saying there are also genus 2 trisections which are reducible. Namely, I take this, or the unbalanced one for S4, and I stick them together, possibly by Meier. So there's a handful of reducible genus 2 trisections, but there's only one more that's irreducible. And so to prove this, what we had to do is we had to think, okay, suppose you throw down curves on the surface so that you have a trisection diagram. Can you find some sort of simplifying sequence of moves that will reduce the trisection diagram to this one? And the main ingredient is a theorem that we almost have seen, but not quite. I studied this theorem when we were talking about bridge splittings, but not when we were talking about Haggard splittings. But what it says is that every genus 2 Haggard splitting of S3 has a wave. Okay. And I didn't define what a wave is for a Haggard splitting. You can probably guess. It's a handle slide. That's a slide of alpha or beta that reduces the number of intersection points between alpha and beta. We stated this as every bridge splitting, every 3 bridge splitting of the unknown contains a wave. I think was the way we stated it. Which this is the equivalent statement upstairs curves when we use this hyperelliptic involution. So if you're trying to prove this, what you see is you have a triple of genus 2 Hagar splittings for S3, and so you know each one of them has a weight. So maybe there's an alpha slide that simplifies alpha beta, but there's a beta slide that simplifies beta gamma, and there's an alpha slide that simplifies alpha gamma, but it might be a different slide than the one before. And so you need to sort of gather all this information together and into a rather complicated combinatorial package and show that in fact there is, we can verify that this trisection that you're handed is actually the trisection described by this diagram. I think that's all I'll say about this. Does anybody have any questions?
How do you tell that it bounds disks in all three intervals?
Yeah, good. Well, do you believe that the purple curve bounds in the alpha angle body?
Yes.
Yeah. Well, the other two are diffeomorphic. There's a diffeomorphism taking the blue curves, this blue and this blue, this blue, this, and fixing that.
And fixing the button?
Yeah.
All right.
Yeah, because
Because it splits into two
Yeah.
diagrams. Okay. All right.
I mean, we kind of talked about this, how you see it symmetrically in all three of them. I think whatever interesting thing we came up with at that point applies. Yeah.
I tend to remember.
that was at least a week and a half ago, so just forgot. All right. Any other questions? Okay, so this classification of low genus trisections. Oh, by the way, maybe I'll just say, we kind of already saw this. I guess I probably already said something about this when we were talking about the classification of three-bridge trisections. Because once again, by using the hyperelliptic involution, three-bridge trisections are equivalent to genus 2 trisections in this branch cover. So I think we stated that three-bridge trisections. There's a unique irreducible three-bridge trisection. It's the same statement as this. Okay. So let's call a trisection standard if it is a connected sum of genus 1 and genus 2, I guess irreducible, genus 1 and genus 2, trisection. And same thing for the diagram. Oh, no, that's not the same thing for the diagram, sorry. I made that mistake when I was writing my notes. The definition needs to be a little bit different for a diagram. Why is that? Or does it need to be different? Maybe I overcorrected. Yeah, I guess it needs to be a little bit different. Because, like, for example, this guy could have. Anyway, let's give another definition. Okay. A Hagar diagram is standard. Hagar diagram sigma alpha 1 alpha 2 is standard if each curve of alpha 1 intersects intersects alpha 2 in at most one point. So for every alpha curve, you either have a single intersection with the beta curves, or you have no intersections with the beta curves. So then a trisection diagram sigma alpha 1, alpha 2, alpha 3 is standard if each Hagar diagram sigma alpha I plus 1 is standard. Okay, so this is sort of like saying the curves intersect Kronecker delta, except not quite. Is there a term for Kronecker delta or 0? Okay, so without loss of generality, our alpha curves look like this. And let's suppose this alpha curve intersects the beta curves exactly once. Then after diffeomorphism, we have this. Let's suppose this one intersects it at one point. But let's suppose this one doesn't intersect the beta curves. So we get this. So another way to say this is a Hagar diagram is standard if it's a connected sum of genus 1 diagrams for S3 and S1 cross S2. And then for a trisection diagram, we also throw the gamma curves on, but they might get thrown on in as a sort of complicated way. That can't be too complicated, that's what you can see. So maybe this gamma curve intersects the beta curves once and the alpha curves once, and same with this one. And I guess this gamma curve could either intersect each of these once or each of them 0 times. So maybe this actually. So I guess another way to define standard for a trisection diagram would be to say that it's the connected sum of genus 1 diagrams with copies of this diagram. Okay. Oh, so I guess I was also going to say this. This is also called simultaneously standard. You hear that phrase from time to time. All right. So, given these definitions, we have the following proposition, which says that a trisection is standard if and only if it has a standard diagram. Okay, so one of these directions is easy. I think this direction is easy. Suppose we have a standard trisection. Well, then we know, I guess, easy. We know it splits as a connected sum of genus 1 and genus 2 trisections, and we know by this result what the genus 2 pieces have to look like.
Standard diagram.
No, I'm saying if the trisection standard, then the trisection splits as a connected sum of genus 1 and genus 2 trisections. And I'm saying each of those pieces has a nice diagram. Sure. And so that's that direction, right? Yeah. Yeah. Okay. Okay. So I mean, I guess this is easy, but it's only easy if you use the classification of genus 2 trisections. But of course, that's the whole reason we made the definition this way. So. So to go backwards is a little bit more interesting because Dave and I consider this a fun exercise. So maybe I'll just give you a hint as to how to prove it. So the idea is now we're going to start with a standard diagram. So you imagine an arbitrary collection of alpha, beta, gamma curves, but they have this really nice pairwise intersection property. And you want to show that, in fact, they all look like either pieces like this, or three common curves, or the CP2. And the hint is to consider chains of intersections. And I was remarking over while I wrote down this proof in the notes all by myself, it was in my head telling me that this is a nice way to think about this. And apparently I learned that. So this is this with a beta curve on the surface. Let's suppose the alpha curve intersects a beta curve. We can kind of transfer to it. And let's also suppose that the beta curve intersects the gamma curve, and so on. We get this chain of curves. Oops. That can't happen, right? That's exactly what can't happen. That's why I did that, the teaching one. What can happen is potential alpha curve. Now it might be that one, but it's your exercise is to worry about all the cases. Let's make it a little bit longer. Okay. So we have this chain of intersections of our curves on our trisection surface. And so what you can do is you can consider, maybe giving away a little bit too much, but okay. Let's thicken this chain of curves to a subsurface. So we sort of follow this around. We get a boundary component. This chain of curves has a boundary component that looks like a degree. Is that supposed to happen? Red, blue, green, red, blue, green, red, blue. Did I cheat? Did I do it right? Not what I expected to happen. Maybe that's okay. Maybe that's okay. So that's one boundary component for this thickening. Let's find another. And so there's another one on the inside. And maybe that, oh no, there's another one. There's another one here. You can tell I just wanted to do this one. Okay. So what you see in this case, there are three boundary components. This is a 9 chain because there's 9 curves. You can check that. Well, the chains will always have a multiple of 3, and if it's an odd number, then there'll be 3 boundary components. If it's an even number, there'll be 4 boundary components. But the point is, this is a fairly interesting subsurface in that it's a big number of curves it contains. Right, so if you do an Euler characteristic calculation, let's see. In this case, you'll get that this thing has genus 4. But that's a problem because it sort of only contains 3 cut curves of any one color. Okay, so that can help you, that's a step in proving that actually no such configuration can exist. And each of these boundary components, I should say that each of these boundary components are rather interesting also because they're curves on the surface that are disjoint from all 3 colors. Right? So either they're essential and they're a reducing curve, in which case you can be done by some sort of induction, or it has to be null on the top. And if they're all null on the topic, then you have a closed genus 4 surface with only 3 recurves. That's the idea of the proof. And what's really cool about this proof is you make this general argument and then it just reduces down exactly to the cases that you're interested in, which is, this is the case of 6-chain. 6-chain. And this is like a degenerate case, and the CP2 is a 3-chain, and the S1 cross S3 is also a degenerate case. It's pretty fun. I'm just going to put a placeholder here in case we have time to the end of the lecture to come back. This would be an example of, well, it's not much of an example. It's going to point you to an example of trisection diagrams that are almost standard, but we don't know. But anyway, I'm going to table that because I want to get through some more important things. Okay. So a trisection T is stabilized if it decomposes as a connected sum with a trisection that I'll denote by Sj, where Sj is the genus 1 trisection of S4 with x of j, or with case of j equal to 1. Okay, so just to jog your memory, what would S2 look like? S2, well, we usually put red here. S2 means the blue-green 4-dimensional piece has complexity, so this is a picture of S2. And there are 2 other ones. So, you know, in Dave and Rob's original paper, they give a stabilization. Well, they get 2 comments. The first is their definition is kind of like how we define it for Hager splittings, where you drill out a trivial arc from one of the handle buttons. And they also considered doing it in all 3 pieces so that the result is balanced. This will obviously change the balance of the parameters, but anyway, maybe it's a good exercise to check that this actually does, this connected summing here actually does correspond to removing a 4-dimensional neighborhood of a suitably chosen trivial arc in your spine. Okay, and then the importance of this is, it's the main theorem of the first paper, which is that any 2 trisections of a fixed 4-manifold have a common stabilization. Where what we mean by common stabilization is I take my 2 trisections inside my fixed manifold and I add on some number of copies of these guys to each one. The resulting trisections become isotonic. And so as opposed to bridge trisections where we had this issue of having perturb and deperturb and perturb and deperturb, this is a straight stabilization all the way to the top, just like with Hager splittings. Okay, so now we can state another good conjecture that you should immediately go out and try to prove or disprove, which is that every trisection of S4 is every non-trivial. Every genus G trisection of of S4 with G greater than or equal to 1 is stabilized. So we don't really know anything about the class, the space of trisections on a given format. Although maybe I can do this also. Okay, two more placeholders or examples. Maybe I'll just go ahead and get one of these. Yeah, let's get this one. So the double branch cover of any 2K plus 1 twist spun 2-knot is S4. I guess this is probably a theorem of Gordon. And so in particular, if we take, but these knots are non-trivial, right? So if you take an odd twist spin, if you take the 7 twist spin of some knot, that's a very non-trivial 2-knot, but the double branch cover sort of kills everything. So you can take what is an interesting bridge trisection of the 2-knot and lift it using the branch covering construction I gave you to get what should be an interesting trisection of S4. So you can ask the question, are all such trisections standard or stabilized, let's say? Standard or even standard. Okay, so we don't really know that. Okay. So I guess I should say that, yeah, maybe I should say a little more about this. So there are other examples of that might be interesting to look at, which come from work with Alex. I guess is pretty recent. Where there exist a bunch of trisections, of type 2G0G trisections for S4 that are almost certainly not, let's say, reducible or stabilized or standard, even stabilized. Okay. And the reason is that these come from sort of complicated constructions of S4, which should only be, you should only be able to simplify these if you can simplify these balanced presentations of the trivial group using Andrews-Curtis moves. And this is something that most people think is not possible. And so, oh yeah. Let me say it like this. Not only are they almost certainly not stabilized, but that are almost certainly not stabilized and even remain non-standard after unlimited 2 stabilizations and 3 stabilizations. Okay. So if you believe that these counterexamples to the Andrews-Curtis, these potential counterexamples to Andrews-Curtis conjecture are counterexamples to Andrews-Curtis conjecture, then you have these trisections that that don't become standard no matter how many times you stabilize these parameters. But by gaining Kirby, if you do all 3 stabilizations, they have to become standard because it is known that the manifolds are S4. So that seems like an interesting class of examples. And in the paper in PNAS, we show you actually, given a fibered ribbon knot, or given a fibered knot, how to explicitly construct fibered ribbon knot, how to explicitly construct trisection diagrams for these things using the monodrome. And we also give in that paper a rectangle condition, which I won't say more about other than just to write the words on the board, which gives a condition on a trisection diagram that is sufficient to show that it's not reducible. The diagram is not reducible. And the idea is that that the trisection is not reducible. The idea is that you take, you expand your cut systems to pants systems for each handle body, and you look at all the intersections of all those curves. And if you can find rectangles of all types, which is a technical condition, then you've obstructed your trisection from being useful. Okay. Last couple of minutes. This is probably where they're going. Okay, so suppose X admits a G, K1, K2, K3 trisection. Then we can conclude a couple of things about its algebraic topology. The first, which I guess has escaped mention until now, is that the Euler characteristic is 2 plus G minus the sum of the K's. And this just follows from the Handel decomposition that you can extract from this sort of thing. And then we get a couple of inequalities based on the same sort of argument. The first Betty number of X, which is less than the rank of the fundamental group of X, which is bounded above by any one of the KIs, each of the KIs. And similarly, the second Betty number of X, which is bounded above by something that I'll call the rank of H2 of X, by which I mean really the number of generators required to generate H2 of X as I finally generated the other group. This is smaller than G minus Ki. And then from both of these, we can conclude that G of X, for example, is greater than or equal to the sum of the first Betty number and the second Betty number. Or maybe more strongly, the sum of the rank of pi1 with the rank of H2. So you get lower bounds on the complexity of trisections coming from the algebraic topology. Okay, and then you can use these lower bounds to show that there are trisections, there are infinitely many distinct four manifolds, there are many trisections of almost any sort. So the statement is that for all G greater than or equal to 3 and 1 less than or equal to K less than or equal to G minus 2, there exist infinitely many distinct four manifolds admitting GK trisections. Minimal GK trisections. And the main ingredient of the proof here is the following fact. Yes, this is also a theorem, the same thing here, which is that if Y admits a genus G Hegel splitting, so Y is a closed 3 manifold, then the spin of Y, which we haven't talked about, admits a 3GG trisection. So the spin of Y, kind of like the spin of naught, is it's almost crossing the 3 manifold of S1, but you either want to puncture it first or surge around a point cross section. So the idea of the proof of this theorem is if you spin lens spaces, or if you spin any three manifold whose rank equals its Hagar genus, then you get a four manifold that emits a minimal trisection coming from this spinning operation. And in order to get all values of K, then you can start adding on copies of CP2. But you can arrange to get everything this way. So there's more information on that in the notes, but I want to skip ahead to some interesting conjectures. So one, every three, so what I'd like to conjecture is that every 3-0 trisection is standard. Probably not very many people believe me when I look for that. The other conjecture I make in that paper is that every 3-1 trisection is every four manifold admitting a 3-1 trisection is a spun lens space. So by this, lens spaces admit genus 1 Hagar splitting, so spun lens spaces admit these 3-1 trisections. So I make that conjecture. And lastly, I want to conjecture that there exist infinitely many distinct four manifolds admitting G0 trisections for each G greater than or equal to 4. Okay. And the reason I want to make these conjectures like this is maybe not what I think is true.
You don't want to say like irreducible G0 trisections? Can you just take kinetic sums of CP2s and CP2 bars?
Well, you
Yeah,
can only
really
get finally many of those.
Oh, I see, for fixed G, for example. Yeah, right,
but-
you're right. No, you're right. That
Yeah.
is not.
Although maybe, I mean, I don't know.
No, it doesn't.
If you can get it for G equals 4, then you get it for all the G by connect sums.
Right.
It's probably wrong, but I don't know. Maybe the conjecture should have been that any G0 trisection is standard. We'd really, well, that's not true.
And we don't know any G for which that's true.
No, we don't know any G for this is true. Although, I mean, I should say that, actually, so 2 comments, I'll just say them out loud because I think I'll talk about them next week. But first is that trisection genus turns out not to be, sorry, what's the way to say this? I said trisection genus is not a homeomorphism variant. What does that mean?
There are manifolds that are homeomorphic, but not diffeomorphic with different minimal trisections.
Yeah, so should I say it's not a complete homeomorphism? Or is what I said right?
Not a homeomorphism variant at all.
Okay, sorry, I'm just.
Yeah, the same because the same underlying. Well, you could define it as a minimal overall homeomorphism class, but.
Okay, sorry. Wait, sorry, explain it to me one more time.
Well,
I'm still.
okay, what is the
So, okay.
trisection genus is a invariant by definition of a smooth manifold.
Right.
Now, the fact that there are 2 smooth manifolds that are homeomorphic with different trisection genus means it is not an invariant. It's not that invariant is not preserved by homeomorphism.
Well, that's we don't know that.
You don't have 2 examples of non-homeomorphic, homeomorphic but not diffeomorphic different. Oh, I see. Then you don't know.
Maybe this is not what I wanted to say. Okay, maybe that's why I'm confused. What's the point? The point is that we do have examples of 4 manifolds that are homeomorphic but not diffeomorphic, but both pairs of G0. So it's not the same as saying it's not homeomorphic. And so what's also interesting about that is that, say for large G, we do get non-standard irreducible trisections of type G0. So for example, K3 admits a 22-0 trisection, and in more generally, like complex hypersurfaces and all types of complex form manifolds admit nice G0 trisections that are irreducible. Yeah, sorry, I got all turned around with that. But that's time for today. So does anybody have any questions?
Example, if those are not stabilized and if there aren't any exotic S4s, then those are irreducible?
So the question of exotic S4s doesn't come into play here. If they're not stabilized, they are irreducible. Yeah, maybe you have to be a little bit careful. In the simplest case, you have 4, 0, 2, 2. And that one, if it's reducible, then it splits into genus 2 diagrams, which we know then destabilize. So reducible would be enough to apply state. I guess for higher G here, you could have that it's reducible, but it splits into 2 other trisections of this type of lower G. Like a 2G prime, 0G prime, G prime, and a 2G, that kind of thing. But exotic S4s doesn't come into play here because these all describe smooth S4s. Although actually you can cook up examples where it's not known whether the S4s, where the homotopy force is. So you can cook up trisections of potential counterexamples to the point grid conjunction. All right, well, that was a lot.